Okay, ladies and gentlemen, welcome to the July 2024 meeting of the Columbus Astronomical Society. A little warm, but get started here. Okay, so I guess we'll start with our Vice President.
How's it going, guys? We haven't discussed this yet, but just to remind you guys, next month is our traditional CAS picnic, and that means we don't have a meeting or anything like that. We just get a bunch of tables out and put them in the side yard, and everybody brings some food, and we just have a nice time. Sometimes people bring musical instruments. It's quite nice, and traditionally we start around 6 o'clock.
Yeah.
And get set up, and then we eat a little after that and enjoy a night of observing after that. As we're starting to, the summer nights are pretty late, and it gets dark pretty late. But if the meeting goes on long enough and people are still sticking around here at the meeting, I'm happy to go out and help people use their telescope if they brought it, or I brought my laser and I can do a sky show and show you where the constellations are and help point things out. Or we can get a telescope out and I can find things. Whatever anybody wants to do, I'm here for that. So I will do that. I'm sure that Mark Peter probably can take part in that as well, or Charles or whoever can help out as well. So that is another thing that we're going to do here. I also edit the newsletter, which presumably you've seen once or twice. I always need things for for the newsletter itself. So if you have anything that you would like to say to the group, you don't have to be an advanced PhD in astronomer to actually write anything for it. I just want to hear what you're into right now. Write me an article about your favorite sci-fi films, or the new astronomical equipment you just bought, or whatever you want to share with the group that you think people will be interested in. It's just primefocus@columbusastronomy.org, and I will get it in there. I haven't gotten a lot of submissions in the last couple of months, so now's a good time. People are not really writing very much during the summertime because we're out doing things. Finally, as the director of the John Glenn Astronomy Park down in the Hocking Hills, we do our programs on Friday and Saturday nights when it is clear. That's kind of a difference between here and Perkins. Perkins will do the programs here even if it's raining, because there's a lot of stuff to look at and cool things to do. We are entirely outdoors at the John Glenn Astronomy Park, and so our show is the sky itself. And so I cancel in the event of rain or clouds and that kind of thing. But on any other night, it's nice to have some folks come down. Mark came down a couple weeks ago. That was great. I appreciate it. And so if you'd like to take part in that, it's not too hard. I mean, if you're kind of new to astronomy and you want to just start getting into this volunteer thing, I'm happy to show you, there's where Alberio is, just point at that, or point at the moon tonight because it's nice and bright. That's good to come out on for the first time when the moon is out, because it's easy to point at with a telescope or that kind of thing. And that's pretty much all I have. So thanks a lot, guys.
Okay, Isaac, you got anything on Cassis or whatever? Okay.
Thank you. So hello everyone, my name is Isaac Cruz. I'm the lead for the CASIS, which stands for the Columbus Astronomical Society Imaging SIG, a special interest group. Long name to basically just describe a bunch of people that like to take pictures of what's in the sky. So if you're interested at all in imaging, what's in the cosmos, talk to me. I'm available every time and any time to actually talk your ear off about imaging. One of the things is we normally have meetings on the third Saturday of the month, but we are in the middle of our summer hiatus. So our next CASIS meeting is going to be in September 21st. So you're all welcome to attend. The meetings are here on Perkins Observatory, actually on this same room, and they usually start about 1 o'clock in the afternoon. They're a couple of hours long, depending on how many questions and depending on the theme and things that are going on. So again, September 21st is our first CASIS meeting restarted. And if you have any questions about imaging, just let me know. I'm here to help you out. Thank you.
Okay, so we have some visitors tonight.
Yes, we do. We have several visitors. In fact, more visitors than vendors, possibly. Yeah, wow.
Okay.
So we have David, Therese, Christopher, and Nathan Shell. There they are. Welcome. And they're for the first time here today, right? Great. And Robin S. Where's Robin? There's Robin here for the first time today. Welcome. And Katie and Brendan Yake. There they are back there. And Teresa Reinhardt. I'm probably saying this wrong. Season. Who's Season? Am I saying this wrong? You came in last. Are they still visiting the ground somewhere? Okay, either. Yeah, they'll be back. Okay.
Okay.
Welcome, everybody.
Yeah. Okay. So now we're going to hear from our host, Don Stevens, who's the director of this establishment, and then he's going to be doing our program for tonight. So I guess we can just segue right into it.
First, like Brad, I wear many hats, and I'll start with my director's hat. And right now, we are on our summer hiatus for programs, although we do have 2 programs coming up the last 2 Saturdays of July called Celebration of the Sun. Those will take place on, I believe it's the 21st and the 30th, or no. 20th and 27th. 20th and 27th. They start at 2 p.m. and they're basically a program all about the sun. We're going to have some solar telescopes out there to observe the sun if it's clear, a rocket launch demo for the kids, and a tour of the observatory, and then a talk all about the sun, things like that. So feel free to come out for that. Tickets are $10 each if you want to participate. If you want to volunteer, then don't need to buy a ticket. You can help like run a solar telescope or something like that, or help with parking. That would be appreciated. And then in August, our nighttime programs resume Friday nights at 9 p.m. through the month of August. And then September, we switch to 8 p.m. because by then the sunsets are a little bit earlier, so then we can get to observing a lot sooner. And I can always use volunteers for that as well, set up telescopes. You don't need to be a telescope expert or a sky expert or anything like that. Just bring your enthusiasm, and we even have some telescopes. If you don't have your own telescope to set up out there, if you don't know what you're doing, we'll pair you with someone, usually a couple of experienced observers here that volunteer, and set you up next to them. They can help you find things and point things and explain to folks what they're seeing and stuff like that. So you're always welcome to come to those as well. Even on a cloudy night or rainy night, as Brad mentioned, we do the programs. So even on those nights, we could use help with parking and just answering folks' questions and stuff like that. So, okay. So I guess without further ado, since I'm the speaker, I'll go ahead and get the talk started. I'm going to do what astro nerds like me love to do, and that's turn off the lights here, so my presentation will show up a little bit better. And so here we go. Well, you may have heard a little bit here on the news recently that sometime this year there might be a new star in the sky. But it won't really be a new star, though. It's new in the sense that, it's not visible to the naked eye, and it's not been visible for a long time. So it's not new in the sense of a new star being born, but it's going to be new to most folks as they look up regularly. If you look at the sky regularly, it's going to be a new star there that you don't recognize. And events like this have been seen throughout history, even since ancient times. And it turns out some of these what they're called nova stella in Latin. Nova means new, stella means star, all right? And that's what it's Latin, by the way. Or novae is the plural. You know, it's not a typo up there with the E, all right? That's how you plural form Latin. And these things I'm going to be talking about called recurrent novae, as the title says, are like the old faithfuls of the cosmos. It's like the old faithful there at Yellowstone. If any of you have ever been out there to watch it, you know, it has a reputation of being a regular kind of geological event where there's superheated water that comes out of the earth and is blown into the air. And it has a period roughly about 44 to 120 minutes or so. All right, it's not as regular as some people think it is. There's some variation in time. But like Old Faithful and Yellowstone, this is something that millions of people can witness as well if they take the time to go out dark skies to do this. And hopefully it'll inspire, just like Old Faithful, awe and wonder. Okay? So we'll take a little bit of journey together to try to understand this unique phenomenon we'll be talking about, recurrent nova, and the related objects. Okay? So start with kind of a little historical journey. As I mentioned, these things have been witnessed throughout ancient times. There's even evidence that as far back as the 14th century BC, these objects have been witnessed, particularly in China. These were often referred to as guest stars because, like a guest, they would show up, stick around for a little while. If they were good guests, they would eventually leave. And these things would slowly fade out to where they weren't seen. Some of them, of course, were significantly bright, so bright that they could actually be seen in the daytime, and at nighttime they would cast shadows. We should note that also that Chinese astrologers that kept track of these things, and that's mostly what they were astrologers, not astronomers, they were keeping track of happenings in the night sky for the royal court, because often changes in the sky could spell ill omen for the royal family, the royal house, or the empire. And some things had good portents, some things had bad portents. And what I got here, this example, this is actually from a text from the 15th century that talks about a pretty famous supernova that occurred in 1054. Okay. Another kind of historic connection is Perkins. He was a gentleman who cataloged the sky, and he invented what we call the magnitude system that we use even to this day. It was recorded by Plinius the Younger, also known as Plinius Secundus, that he had witnessed a new star in the sky, and that had inspired him to catalog the stars in the sky back in the 2nd century BCE. Now, in Europe as well, they were interested in new stars because of the influence of later on the influence of Christianity, because a star was, particularly the Star of Bethlehem, was the sign of the arriving of the Messiah. They often thought that new stars represented actually something good happening, unlike comets, which often would symbolize things bad happening. Getting closer to more modern times, what was discovered one morning was Perkins here. He was actually looking for Mercury, doing some observations of Mercury, and he thought he saw a new star, and he called it a nova. Well, it turns out like a year or so later, he looked, and right in the same part of the sky, it appeared again, and it turns out this was one of the first true variable stars that was discovered. He nicknamed it Myra, which means wonderful. It opened up a new kind of chapter in astronomy as well, where before astronomy was more concerned with the planets, the positioning and motion of the planets, it started to refocus a little bit on the stars themselves. And then we get a little bit further into more modern times, by the early 1900s, at that point, throughout looking at historical documents from different cultures, things like that, a little over 100 by the early 1900s of these new stars were cataloged. And then later on, though, with the invention of the telescope, more focused studies of the sky and surveys of the sky, and particularly surveys with telescopes, since the 1900s, there are now thousands, tens of thousands of these things have been cataloged. So what are some early ideas of what these new stars were? Okay, there were many hypotheses out there that what these things could possibly be. One of the earliest thoughts were they were colliding stars. Two stars that would collide together and would dramatically brighten for a short period of time. Now, this does occur. It's actually very rare there because, well, space is huge. The average distance between stars and the Milky Way is about 7 light years. That's a lot of space relative to the size of a star, which is only about 1 million miles wide. So collisions are relatively rare. They do happen more commonly in the center of like globular clusters or centers of galaxies or things like that. Amazingly, during galaxy mergers, again, very few stars will actually collide in that situation because the distance between stars allows essentially the galaxies to kind of pass through each other without many stars colliding. But this didn't, so in other words, this doesn't explain the frequency of nova that was observed. All right, you might see one of these events in any particular galaxy, once 1,000 years or so. Another thought was, well, stars were moving around the galaxy sometimes that they pass through like gas. It's called the nebular gas theory. That they would somehow ignite the gas around them and dramatically brighten for a short period of time. Although, again, this would be rare for this to actually happen. It wouldn't explain the frequency of novae. And here's an actual example of a star passing through a nebula, and it creates essentially a bow shock because stars, they emit these stellar winds as well. And it would push the gas away before it would accumulate and ignite on the surface of the star. Another idea was inherent instability in the star, where the star would just, for some reason, become unstable and detonate. That, again, was very unlikely in smaller stars. There are supermassive stars. This might possibly be one mechanism that leads to certain types of supernovae. But again, very, very rare that there are stars that would be massive enough for this to happen, often to explain the amount of novae that are observed in our galaxy. So now we can take a little bit of a journey to try to see how the pieces came together to understand what novae are. And we start with actually something that might seem on the surface unrelated, and that's something called accretion theory. All right, and it's more commonly known and understood in terms of formation of planets. In particular, one of the early hypotheses was put forward by René Descartes, who you might be familiar with, who created like Cartesian coordinates and famous, he's also did a little philosophy, I think, therefore I am. He postulated that the universe actually was filled with vortices of particles, and some of these vortices of particles condensed down to form the sun and planets. Later on, we had a gentleman named Swedenborg and also Immanuel Kant and Laplace all hypothesized that that is actually in these nebulae that were observed through telescopes, that this is the place where solar systems were condensing and forming. And they would basically form out of these disks of material around stars. And it was much later that, actually another thing, it played a lot into what was called the spiral nebula debate. observing these spiral nebulae in the sky, and telescopes didn't understand the nature of what they were. Here's an example like is often referred to as the Andromeda Nebula. All right, and of course now in modern times we know that these are separate galaxies. It was Hubble that pieced that together. But that debate was about the nature of these things. Some people believe that these were solar systems in the process of forming within the Milky Way. Others believed that these were extragalactic island universes like the Milky Way itself. As I mentioned, basically Hubble's the one that settled that. And then modern accretion theory basically be traced back to this gentleman, Victor Severnov, in the early 1970s, who pieced together the mechanism for planet formation and things of that nature. Another set of clues comes from the discovery of binary stars, and in particular, Herschel did a lot of work in cataloging and binary stars and showing that they are indeed physically orbiting each other. A lot of these stars are physically orbiting each other, and they obey Newton's laws in that they often orbit a common center of mass between them, or center of gravity. So another thing Herschel helped with is in terms of the discovery of white dwarfs, and he found first the star called Eridani, 40 Eridani b, right here, and showed that these two stars were orbiting each other. He didn't really at that point appreciate the fact that that was significantly dimmer than the primary star in the system. He was just more interested in the fact they were two stars orbiting each other. He didn't question the nature of that other star. It basically was other astronomers that started to puzzle out what this other star was in relationship to normal stars. Also Bessel, he did mathematics, also his famous Bessel functions. He discovered what he called it a dark companion to Sirius. He looked at the proper motion of Sirius over time and noticed that it didn't follow a straight line. It had this kind of wobbly path, and he hypothesized there was actually a dark companion orbiting Sirius, again, about a center of mass, center of gravity, causing it to take that path across the sky. That wasn't visually detected until Alvin Clark in 1862. The telescope was able to visually observe that companion. And again, it was a dim white star that he observed. And generally, when you discover a binary star, you call one component A, the other one B. So this was often referred to as Sirius B. And then Otto Struve was one of the first ones that started to think about the unusual properties of these stars, noting that these stars appeared to be, at least appear to have the same temperature as the primary stars, so they should have the same brightness if they're at the same distance, but they didn't. So he started to point out that there are some weird properties about these little stars. And it was later that another astronomer, John Gore, basically, as telescopes got better, they could do more precise measurements of these objects. And he was able to figure out that this thing, in particular Sirius B, if it was as small as it appeared to be, but yet appeared to have about the mass of the sun, this thing had to have incredible density. In fact, it worked out to about 43,000 times the density of the sun. And you can see here, the average density of the sun is about 1.5 grams per cubic centimeter. It's roughly about the size of a sugar cube. It's roughly about the density of corn syrup, as I mentioned there. But the sun's density, of course, varies from its surface to its interior. This is just the average density I mentioned. It gets as high as 160 grams per cubic centimeter. So a little over a kilogram in a very small volume. Human body, because we're made of mostly water, is roughly about 1 gram per cubic centimeter. The Earth is about 5.5 grams per cubic centimeter, and lead is about 11 1/3 grams per cubic centimeter. Okay, so this thing is incredibly dense. The first good spectrum of one of these objects was done by Wilhelmina Fleming. She got a spectrum of 40 Eridani B. And this is a more modern spectrum, though unfortunately the lines don't show up that well on the projector here, but it has very strong lines here of hydrogen. All right, and the spectrum pretty much looks identical to a normal A-type star, which again was kind of mystifying to astronomers at the time. And then later, Hertzsprung Russell, when they put together a famous HR diagram plotting the brightness of stars versus their temperature. And what you'll note is the way they plot it, this is from their original paper. Since now we plot it the opposite way. And this, instead of having temperature increase this way on the x-axis like you normally do, when you're plotting things on an x-y axis, they plot temperature increasing going this way now. So the main sequence tends to run this way in modern HR diagrams instead of this way. But what you'll notice, this little guy over here by himself, that is 40 Eridani B. And again, that alerted them that there's something unusual about these stars. Oh, again, here's a more modern, HR diagram again here. Hot temperature, cool temperature, and then brightness increasing along the y-axis. Most stars fall along here, what's called the main sequence. There's our sun there. And then this region is where we find white dwarfs. And then Walter Adams got, with the 60-inch telescope, got an even better spectrum. Again, you can see these strong features of hydrogen in the spectrum. This is of Cirrus B. And then this is an image of the first isolated white dwarf that was discovered in 1917, the Manin star. And what they would often do is, when you take a picture of part of the sky to see if anything's moving, you take it in either one color filter, then later in another color filter. In this case, a red and blue filter. And if anything's moving, then the colors aren't going to stack up on each other to make white. You're going to see that there's indeed motion that way over time. And then this is the first image of Cirrus B through a telescope. And it looks like a diagram, but this is an actual image. And the way because Cirrus B orbits so close to Cirrus A, what they had to do was basically put a special mask on the telescope that was hexagonal shape. And what that does is create diffraction spikes that stretches out the image of the star of Cirrus. And then you can rotate it to move those diffraction spikes out of the way. And there is Cirrus B right there. Okay, and it took until 1970 to figure that out and do that. And then we get to Arthur Eddington, who's a very, very famous astronomer and associated with Einstein and Chandrasekhar and many other famous astronomers and physicists and things like that. He, at a meeting, called attention to these strange objects and tried to basically get everyone in the astronomical community to focus on this problem to figure out what these things are. He called these things strange objects. We need to understand what they are with these unusual properties. And then Leighton here, he basically was the guy that in a paper was the first to use the term white dwarf. Before that, they were just called strange objects or strange stars, all kinds of things like that. So, but what exactly are white dwarfs? All this time I've talked a little bit about them, but I haven't explained exactly what they are. And that basically begins with, actually in the early days of quantum mechanics, it turns out to solve this problem you require quantum mechanics. And this was actually, he was the first one to apply the new science of quantum mechanics to its first practical application, and that is towards these strange stars, white dwarfs. This was, he basically applied a branch of quantum mechanics called quantum statistics to solve this problem. So let me do a brief introduction into quantum mechanics so you understand the problem and how we come to figure out what these things are. We actually start with Einstein, who famously often was opposed to quantum mechanics, but he's in a sense one of the fathers of quantum mechanics. During his miracle year of 1905, one of the papers he published was on the photoelectric effect, and basically describing how light comes in these little packets called quanta, and that's where the word quantum mechanics comes from. And that paper turned out to be so important that now there's many technologies that we have that's based off this photoelectric effect. Like you go to the mall, and as soon as you walk in the door automatically opens. Well, that's using actually that effect to activate a mechanism to open those doors. Okay. And then there's this gentleman named Louis de Broglie, who basically from that postulated that not only light should behave like this sort of a pseudo-particle, pseudo-wave thing, but that matter should as well. And he formulated, based off of Einstein's work, this thing called the de Broglie relationship that shows that basically the way that particles relate to waves and vice versa. And then later on, and then basically, the particles come in what are called wave packets. Sorry, I got a little ahead of myself. Particles come in wave packets. All right, they're not true waves like light and such. They travel in these little things at what are essentially enveloped in an envelope that are probability waves. All right, so the particle's not located in any one position, so this expresses more the probability of where a particle is. And Edwin Schrödinger formulated his famous equation that in the end talks about the behavior of these particles. And there's been many experiments to show that this is the case. A good example is Thomson fired electrons through basically a bear with a slit in it, and produced these diffraction patterns like you see with light. Okay, and basically showing that these electrons do indeed behave like waves, like light does. I did this experiment myself. This is often used to shoot through a material to look at the structure, the atomic structure of material. This is graphite. Basically shooting a beam of electrons to the graphite, and basically you can essentially see the atomic structure of the material. And then, of course, there's the Heisenberg Uncertainty Principle, which I know many people have heard about. And what I'm going to do is I have a little demo here to demonstrate it. All right, so what I'm going to do first is, let me blank the screen here. Then I got to go to the back of the room, and then I'm going to project something on the screen here from the back of the room. So what I have here is a laser that I'm going to shine through a slit. And then actually, tell you what, let me turn this off here. Oh, I'm sorry, I got it. And then what you're going to see is a diffraction pattern. Now, as I change the dimensions of the slit, all right, you're going to see the diffraction pattern change, because as the Heisenberg Uncertainty Principle that was expressed in the equation I had up there, delta x times delta P, which is the momentum, is equal to or greater than h bar over 2. All right, that's a constant, which means if I change x, all right, if I make x bigger, P has to get smaller in order to maintain that constant on the other side of the equation. And if I change P, that means, if I make P bigger, that means x has to get smaller. So actually what I'm going to do is the light particles coming through here, the quanta, the photons, they have momentum. Okay? And as I restrict, though, delta x, the width of the slit here, you're going to see the diffraction pattern change in response. In other words, the momentum of the photons has to change, all right, as I change the dimensions of the slit. So let's try this. So as you can see, they change. I'm making the slit wider. Now, if I move it the other direction, watch what happens. I'm making x smaller. The momentum, the uncertainty of momentum gets bigger until I close it. And what I'm going to do now is I'm going to put a green laser and do the same thing, because the green laser, the photons have a shorter wavelength, they have higher momentum. And it should be a more dramatic effect. Okay. Okay, let's see. Yeah, I didn't have it quite, hold on, I don't have it quite lined up. Here we go. So, here again, I'm going to change delta x, and delta P is going to respond. All right. So that is the uncertainty principle demonstrated with light, but it applies to particles as well. And then the final piece of the puzzle here is something we call particle in the box. All right? And, whoops, sorry, I forgot to turn my screen back on. Okay, and I have a little software demo that's going to demonstrate this. Come on. There we go. All right. So this has a one-dimensional and three-dimensional representation. All right. We call this, it's based off a thought experiment called a particle in a box. And what happens is, as we change the dimensions of the box, all right, it's going to influence the behavior of the particles. Okay. And so let me see here. Unfortunately, I have to do this over my shoulder. Now, what I'm going to change here is called the quantum number. And this could be the spin of the particle. This could be the energy of the particle, some property related to that. And then what you're going to see is the number of peaks. Again, this is an expression of probability of where the particle is going to be in the box. All right. And what you're going to see, though, is like, you know, how many wavelengths can fit in. That's another thing it could be related to, is how many wavelengths. So right now, let's set quantum number 1, but let's go to 2. All right. All right. So, you ask, what does this have to do with white dwarfs? We'll get to that here in a moment. But I just wanted you to see this, all right, this little demo. And then another piece of this is something called, let me switch back to my presentation. That's not the right one. There we go. It's called the Pauli exclusion principle. All right, and again, this is something that is important to not just physics and the things I'm going to be talking about, but it's basically the basis of how chemistry works as well. And that has to do, I'm sure many of you, if you took a chemistry class in school, you learned about the different elements on the periodic table and how many electrons you could have in each orbital and things like that. Well, that's governed by the Pauli exclusion principle, all right? And you basically can't have two particles in the same orbital that have the same spin, all right? So, for example, you have a hydrogen or a helium atom that has 2 electrons in the first orbital. One has to be spin up, one has to be spin down, all right? They can't be both spin up or both spin down, all right? And there's just no way to force that kind of violation or anything. It's a fundamental part of nature. So, now we're going to talk a bit about nuclear fusion is an important part of this as well. All right, basically how stars do their thing. And it goes back to one of the big mysteries of the late 1800s, early 1900s was the age of the Earth. There was a big debate between geologists and biologists and astronomers on how old the sun was, how old the Earth is. All right, geologists and biologists were saying the Earth was millions to billions of years old. However, astronomers thought that, well, the sun, for example, got its power it got its power from either gravitational collapse or the heat of its formation or being bombarded by meteorites. All those things, though, produced the lifetime of the sun as being only tens of thousands and maybe hundreds of thousands of years, not millions and billions of years. The Earth be so old and the sun wasn't. All right? And the puzzle started to be solved first, again, from more the chemist direction, and that is particularly Recurrently here, who discovered radioactive decay, basically discovered radiation, radioactivity. And he had to basically set a sample of a rock on film and develop it, and basically this is that image, the first image of, it's basically, you call it the shadow of uranium, okay? So he discovered radioactivity. And that allowed the possibility of an older sun, because you could figure out what's called the half-life, how long it takes half of a sample of a radioactive element to decay away, and that's called the half-life. In the case of uranium, that's about 4 billion years is its half-life. And so that, if the sun was powered by that, that would allow enough time for the sun to exist and thus have an older Earth. And then, again, basically Robert Bell, he basically postulated that that's what the case. The sun is actually indeed powered by radioactive decay. And then Stark here went on so far as to say that not only was it powering the sun, but it was also the origin of the elements. His idea basically was that the elements started with uranium and it would decay down to form all the other elements in the universe. It was still Eddington, who I mentioned earlier. He's the guy that figured out that it must be in this process called nuclear fusion, which is the opposite of decay. And basically, with nuclear fusion, that's where basically you take 2 protons, in this case hydrogen, they fuse together, they release a tremendous amount of energy, and eventually you produce helium from. It's called stellar nucleosynthesis, and he's the origin of that idea. It basically explains several of the properties of the sun as well, and it again allows for the sun to be old, billions of years old, and can accommodate an old Earth, basically. Okay. Now, how does fusion work, though? I got again another little demo here I want to show. All right. It actually, again, requires quantum mechanics. All right. In order for this fusion to take place, the object has to be hot enough to give the particles enough energy to fuse together. Because protons are both positive, they want to repulse each other. It's called the Coulomb force. Okay? And you basically have to get a proton going fast enough to overcome that repulsive force to get them close enough then where the strong nuclear force, which is an attractive force but works on very, very short distance scales, for that to overcome the Coulomb force and for those protons to merge together to eventually produce a helium atom. Okay? And that process, though, without quantum mechanics, would take a temperature of hundreds of billions of degrees. Okay? But the sun, at its core, is only about 10 billion degrees. So its temperature would not be high enough to get the energy enough for those two particles to stick together. All right? Couldn't get them close enough together. So it requires a process called quantum tunneling. Okay? And what we have here, this is the barrier. And what I'm going to do is basically send a particle. Let me reset here. Towards the barrier. And if the energy is not sufficient, what's going to happen? Well, it's going to be essentially repulsed. So the particle is not likely to penetrate the barrier when the energy is low. And that's basically what this is showing, again, not the particle itself, but its probability of where it's located. However, if we increase the energy, i.e. get the temperature high enough, oops, what did I do? As you can see, there's a good probability that the particle will penetrate the barrier, right, and fuse to form helium and release that extra energy. Okay? So it's a quantum process that powers the sun as well. Okay? So where do they come from? Well, basically white dwarfs are formed as a result of stellar evolution, right? Stars, we now know they form from these big gas clouds called nebula, all right? And depending on how big the star is, determine its fate. We say mass determines the fate of the star. All right? The vast majority of stars are low mass, so and like the sun's a low mass star. It's slowly burning its hydrogen and helium. It's going to build up a helium core and eventually swell up into a red giant. And then briefly it'll produce some carbon and oxygen and will, in the core of the star, that carbon-oxygen core, will form the white dwarf, and it'll blow its outer layers and form some of the beautiful planetary nebula that we observe through telescopes, like the Ring Nebula that's up there tonight. If the star is very massive, all right, I'm not really going to go much into this, of course, for this talk. The star could explode as a supernova and form a neutron star or black dwarf. Now, what happens in the center of the star, as I mentioned, it'll build up this core of carbon and oxygen, and eventually what happens is it'll form a state of matter called degenerate matter, all right? Because of the pressures at the center of the star, due to its mass, is going to start forcing the atoms closer and closer together as that carbon oxygen core builds up. And eventually, what will happen, it confines the electrons. It makes that box smaller, as I mentioned. All right? And what will happen is the electrons then will start to fall in and fill in these energy levels. All right? And they will do it in pairs. All right? And again, one will be spin up, one will be spin down. They fill all the available energy levels they can from the lowest to the highest energy level. Where normal gas, a lot of the energy levels are available and free, so the gas can take on whatever energy it wants to at that point. But as you squeeze it down and confine it, it becomes very limited as far as what energies these things can take on. And so they pair up and they stack up into these different energy levels. And that's called degenerate matter. Now I have an example here of degenerate matter, which I will pass around and let you check out. Now, this is very heavy. It's degenerate matter. Okay. Here. You want to take it?
No,
It's really heavy. You ready?
probably not.
It's not. It's aluminum. But it is degenerate matter because the electrons are in a gas form in the metal. All right? The valence electrons, the outer electrons, and they are all arranged at different energy levels. This is basically what makes metals conductive as well, is because they're at these certain energy states and are free to flow through the material when you apply a current. All right, it lets these things fly through the metal, move around. That's how we generate power and send electricity across the continent through wires and things like that. So, but those electrons, and that's also what makes the metal so stiff as well, is those electrons, those free electrons in there, and makes the metal shiny as well. Okay? Normal matter behaves a specific mass-volume relationship. If you add mass to something, its volume gets bigger, right? If I have a bucket of half full of water, I pour more water in it, right? It's going to fill the bucket, right? Well, degenerate matter actually behaves differently, all right? If we add more stuff to it, it actually gets smaller. All right, and that is because part of general relativity states that gravity, or pressure, it's a kind of energy. And energy in general relativity gravitates. It generates a gravity field. Not just matter, but energy does as well. And so, since pressure is energy, it increases the amount of gravity. And so, as you add more mass, you increase the pressure, and thus the volume is going to get smaller. All right, so very counterintuitive how it behaves. The structure of white dwarf, well, there's several types of white dwarfs, and they have slightly different structures. Most of them have a core of carbon and oxygen, as I mentioned, but some of them will have like an outer sheath of helium and then hydrogen. Sometimes it's neutral, sometimes it's ionized, depending on the temperature of the white dwarf. And there are some that's not pictured here. There are some that are called helium white dwarfs that are basically just pure balls of helium. These are more formed by very low mass stars that don't fuse carbon fuse helium into carbon and oxygen. And we could tell what their composition is spectroscopically. We can basically look at the star spectrum through telescope. Yeah. You got it okay? Your back okay? Yeah. We can take a spectra of these things and determine what type of white dwarf it is from the spectra. So some basic stats of white dwarfs. They basically range anywhere from about the radius can be about anywhere from about 0.08 to 2% the radius of the sun. The Earth is about 9% the radius of the sun. So they could be a little bit smaller than Earth to bigger than the Earth. Their masses range anywhere from a little over a tenth of the mass of the sun to 1.3. That's some of the largest ones we found, about 1 1/3 times the mass of the sun. Temperatures range from about 10,000 degrees or 10,000 Kelvin to 100,000 Kelvin. And their densities anywhere from 10,000 grams per cubic centimeter to 100,000 grams per cubic centimeter. So putting all the pieces together, all right, this started to happen actually in the 40s, 50s, and 60s. In particular, Walker here found that this particular nova that had exploded back in 1934, called DQ Hercules, found it was a binary system. And these are actually the eclipses from its, where one star is eclipsing the other as they orbit each other. This gentleman, Robert Croft, he basically put together a theory paper that outlined, showing several lines of evidence that pretty much all types of what they called cataclysmic variables, not just novae, are formed basically in a close binary system involving a white dwarf. Okay. So what actually causes the nova outburst, though? What causes nova to happen? Okay. Well, as mentioned, basically they're binaries, right? And they come, we start with close binaries. What you'll get is a case of two stars orbiting each other, and they orbit very close. Sometimes they can be so close that they are actually in contact with each other. These are called detached binaries, semi-attached binaries, and attached binaries. And this can influence the evolution of both stars. All right. What will happen is, as stars evolve, eventually one of them will, if their masses are slightly different, they're going to evolve at different rates. Bigger stars evolve faster, so the bigger stars are going to swell up into a red giant, and they might envelop each other. It's called common envelope. They're basically two stars are going to be inside a big envelope of gas around each other. And eventually, though, that envelope will get blown off, and then what you'll be left with is white dwarf core of the first star that evolved. And then you'll have, its partner will be a main sequence, and eventually that star, again, it'll evolve. It might swell up into a red giant, and then you might get another common envelope phase, or you might get a situation where a star basically, they become symbiotic, and it starts pulling material off the other star. And this could result in one mechanism for a certain type of supernovae called type 1a supernovae, but it's definitely influenced in nova eruptions. So yeah, and then what'll happen is, like I mentioned, then it'll start robbing, the white dwarf will start robbing material off its partner star. All right, and I got a little thing here to show. All right, this is kind of a schematic that shows, this is, if you take and plot the gravitational potential field, all right, and that's what this plot is of. It shows basically the gravitational field, and you'll have these points, they're called Lagrange points. They're stable or semi-stable points gravitationally between the two bodies. And the one in between the two is called the L1 point, or Lagrange 1 point. And that is where, when the other star, when it evolves and swells, it'll basically begin to spill material through the L1 point, and then it will fall onto the white dwarf, often going into orbit around it first, forming what's called the accretion disk, which again, where the accretion comes in. And that material then basically starts to build up on the primary, and we often call the white dwarf, in this case, the primary star. And on its surface, you'll get a fusion reaction because of the gravity of the white dwarf is going to compress that layer of hydrogen that's building up on the surface. That layer of hydrogen, by the way, builds up to a few meters thick. I mean, literally about, maybe at most the height of this room. And at its base, you can get hydrogen burning, and what'll happen then, that can actually become explosive, and then you essentially get the fireball phase. So a little movie here that's supposed to, oh, it's telling me it won't play it. Why won't it play it?
Is there a correlation between the white dwarf size and how quickly it begins to burn that material?
Wow.
Like from the other star?
Get in that. You're anticipating a question.
Sorry.
Yep. But anyways, this will become violent, and it'll blast that layer off the surface of the white dwarf and expand as a fireball and cool over time. And then the star will go into a period of quiescence where the creation process will start again, and it'll start building that material up on the surface. Okay. There are different types of these. All right. The two main thing about novae is astronomers basically over time have developed a specific definition of them as far as their what we call a novae versus a supernovae. Novae typically get up to an absolute magnitude of -6 or -7. What absolute magnitude means is if I take a star and put it at 10 parsecs away, which is about 32 light years away, how bright would that star look to the naked eye or through a telescope? If you could see it naked eye, how bright it'd be or whatever. In this case, it'd be -6 or 7, about the brightness of the first quarter moon. All right, so they can get pretty bright, or about 10,000 to 100,000 times as bright as the sun. Comparison to supernovae, which get much brighter, and they can be more than 100,000 times the sun, and they can even outshine the entire galaxy that they're in. This is supernova 1987A, and by the way, this other one was the one that was in Delphis a few years ago, Nova Delphi. And of course, over time, you learn that there are often subcategories of these things. Of course, classical novae is the broad term of just these stars that explode. They only appear to explode once, and they come in different flavors, of course, as well. You have fast novae, which will rise in brightness very quickly and decline in brightness very quickly. And an example of that is one that happened in 1975. There's more slow, which again, this is DQ Hercules I mentioned earlier in 1934. And well, for fast novae, they will rise in a matter of a day or so, and they will drop to 3 magnitudes less than 100 days. That's where we classify as fast novae. Slow novae, the decline of 3 magnitudes takes more than 150 days at least. And then there are these very, very slow novae that can take thousands of days for their brightness to decline. This is another example from one that happened in 1967. Now, here's the schematic of the typical light curve of novae. They usually brighten by about 9 magnitudes, and then they'll, for some reason it's not exactly understood yet, they pause briefly in their increase of brightness, and then over the next day or so, then they'll finally make the final climb into maximum brightness. Then they have the decay period, and then you can get 3 different things that'll happen during what's called a transitional phase. It'll either just continue to decline, or you'll get these kind of periodic fluctuations. Might have to do with some instability in the accretion disk resuming accretion, and it might have something to do with some dust formation. And you also will get this dramatic dip that occurs that is due to dust formation. In other words, material cools, condenses down, forms these little dust grains that temporarily obscures, and then as this expands, then it becomes more optically thin later on, and then will resume its normal decline in brightness over a period of years. Then there's another class called dwarf novae, which means they basically don't get as bright. The mechanism for them, though, is just this has to do with instability in the accretion disk itself. What they think happens is the temperature increases to the point the viscosity in the disk changes, and this really will dramatically increase the amount of accretion onto the star's surface and will cause this kind of flaring and small brightness changes. This is an example one called SS Cygni. And then recently there's these things called micronovae that are kind of subluminous novae outbursts. And then there's the primary subject of the talk tonight are these recurrent novae. Okay? And could it be from years to decades? For example, T Brodicis here, has a period anywhere between 12 to 44 years in its outbursts. Some of them, the periods seem to be a little more regular. Others have a more widely varied period as far as outbursts. And one thing they think is that all novae in the end might be recurrent. It just might be the periods are much longer than these typical recurrent novae. They might be periods of 1,000 to 10,000 to 100,000 years between outbursts. And so the star that is being made a big deal of in the media right now is called T Coronae Borealis. Its first confirmed definite observed outburst was 1866 by John Birmingham here. Here's the light curve in the green here. It was only seen when it was at maximum burst. It wasn't really noticed before then. But since then, we've kept pretty good track of its brightness. This is the further 1946 outburst, which had a couple of interesting features, which will be important here in a moment I'll go into. It particularly had this pre-outburst dip that was observed in the star's behavior. The schematic of the system and the basic stats, this is what we think the system consists of. It's a red giant star with a white dwarf pulling material onto an accretion disk here. The mass of the white dwarf is about 1.37 maybe. We're not sure of that one. Its mass. And the secondary, it's a red giant of M spectral type. It is about a little over the mass of the sun itself. Its temperature about 3,600 degrees. The orbital period, the period that the red giant goes around the white dwarf, is about a little over 200 days, 227 days. And they're separated by about half the distance between the Earth and the Sun, half of an astronomical unit. And the system in the sky, is, if you could see it, its orbit's inclined towards us by about 67 degrees, and it's roughly about 2,600 light years away. It's normal at about 10th magnitude, almost 11th magnitude visually, but when it goes nova, it can get as bright as 2nd magnitude, naked eye visibility. Now, again, they're thinking it might go nova this year. This is data from the AAVSO, and it's showing that kind of pre-outburst decline that was observed in 1946. So we might be getting into the early phases. This was at the end of 23. I think it's leveled back off since then, which it did the same thing back in 1946. And there are other recurrent novae. Some examples are Scorpii, Iris, Ophiuchus, and Ci Aquila are some other examples that you can look up and also observe regularly if you want to see if you can catch them in their next nova outburst. Now, as whether or not nova are linked to supernova, it's kind of a question right now. Exactly, because some think that when the nova outburst occurs, it blows material off the surface. It might actually blow some of the white dwarf material off as well and actually decrease the mass of a white dwarf in this case. But what they think for type 1a supernova is you basically, the star will build material up on its surface, increasing its mass, and it'll reach a certain critical mass, referred to as the Chandrasekhar limit after this gentleman, who in 1931 calculated this. What he discovered is, well, I had mentioned how when you dump matter onto a white dwarf, it shrinks in radius, right? Counterintuitively, well, if you don't treat it, the forces going on inside the star using special and general relativity, you can basically just keep dumping matter on that star and it'll get smaller and smaller and smaller. But because the universe, well, does use special relativity, and in particular, those electrons that make the gas degenerate inside the star, as I said, they're confined around these atoms as the atoms get crushed closer together, making the box smaller. And just like I showed with the demo there, all right, when you confine the size of the box, the momentum has to get larger. Well, that means the electrons, if you confine them smaller, their momentum has to get larger, right? So they start moving faster. And what happens is you'll reach a point where the electrons essentially become relativistic. Their velocity approaches the speed of light, all right? And the star can no longer support the pressure of the extra material, and it triggers a collapse, all right? And he calculated it to be about 1.4, 1.44 times the mass of the sun. It's called the Chandrasekhar limit. One thing that could happen, all right, we're not sure, it could collapse into a black hole, it could collapse into a neutron star, but another thing that can happen, and we think what might happen before it actually reaches the limit, is it goes through a process called deflagration. And it's basically the star explodes, goes through a rapid thermonuclear burning the carbon and oxygen into iron, and the star basically consumes itself. And this is a simulation showing that process. It's different than detonation. Detonation, the explosive wavefront travels faster than the speed of sound through the material. Deflagration, it travels slower than the speed of sound through the material. So this is a model showing the deflagration of a star. And this can happen below the mass limit, which might explain certain type 1a supernova have been observed to be underluminous, and they think the progenitors are under the critical value. And as an aside, it turns out actually there was someone else working on this problem as Chandrasekhar was. Chandrasekhar, he was traveling from India by ship to England, and he was doing all this work that eventually would publish in a paper when he arrived in England with the help of Eddington. But at the same time, Edmund Stoner here was working on the same problem and arrived basically at the same solution at roughly the same time. So if you want to observe novae, particularly at T Coronae Borealis goes off, it could be happening tonight, you never know. Here's what you'll need, okay? Basically, you need to know where to find it, okay? And this is a section of the sky where Coronae Borealis is located between the constellation of Hercules and Boötes. Boötes has a bright star Arcturus, and then bright star Vega is over here next to Hercules. And Coronae Borealis, that means the northern crown, all right? And it's basically a small arc of stars with one bright star, kind of like the jewel in the crown right there in the center, okay? And you'll need actually some good finder's charts, though, in particular to find where T Coronae Borealis is. All right, so here's the constellation Coronae Borealis. That's the bright star in the crown. There are 1, 2, 3, 4, 5, 6 stars in the crown. It's going to be if you're looking up at it, it's going to be you go to the third star over. You might need binoculars to be able to see these if you're like in suburban light polluted skies. You basically point the bright star in the crown and look for the third star to the left if you're looking at it. And T Coronae Borealis is going to be nearby. And if you go to the AAVSO website, they have charts specifically for the star, kind of zoomed in. So there's that star, and T Coronae Borealis is going to be nearby. When it's in its normal state, it's going to be at a limit to where you need a telescope to see it. You're not going to even see it through binoculars, okay? Only when it goes in outburst are you going to see it in binoculars or naked eye, okay? But this finder chart will help you identify it once you have a telescope, all right, and you point in that region. And what you're going to do then is with these charts, they have the magnitudes labeled here for various stars around that you can compare the brightness of it too, making a comparison and estimate visually the magnitude of the star, okay? And so get yourself a notebook and make your recording of what star you think it's close in brightness to. And then you can, with your binoculars telescope, like I said, it's a helpful tool. And then you can report it to the AAVSO, and you basically are contributing to science that way as well. All right, they find those observations, even the visual ones, useful. Okay? So, now, questions? Yes?
When the red giant blows up, it goes nowhere.
Well, in particular, like the red giant in this system, it's about the mass of the sun. It's not going to blow up. It's going to evolve eventually to a white dwarf planetary nebula as well. But it depends on how long it takes for the material to be pulled off the star as well. It could take, 100,000 million years, something like that. Yes?
How do you get these two different types of stars? I mean, it sounds like they could be different ages, but how do you get them?
Well, generally they form together. The binaries form together.
So they evolve together?
They form together, but they don't evolve at the same rate because mass determines how fast they evolve. Bigger stars burn their nuclear fuel faster because there's gravity is stronger, they're compressing more, the core temperature is higher, so the fusion's happening at a quicker rate.
So the white dwarf was initially larger.
Right. It was the more massive star, that's why we still call it the primary star. Yes?
When you had that explanation of the laser going through the slit,
Yeah.
the diffraction, I'm sorry, I'm still slow to understand what the significance that is for this topic.
Well, basically, it was mostly to demonstrate how the uncertainty principle actually works. All right? And in terms of also the electrons in the white dwarf, the degeneracy of the white dwarf, again, the size of the box, all right, let me go back to the actual equation. almost there. Yeah, oop. Okay. So this is the equation for the Heisenberg Uncertainty Principle, all right? It's delta x times delta p is greater than or equal to h bar over 2. H bar over 2 is a constant. So that means that if I manipulate something in this side of the equation, right, no matter what I do here, this has to be the same value. So if I change x, if I make x bigger, p has to get smaller. If I make p bigger, x has to get smaller, or vice versa. All right, and what happened with the slit is I made the slit narrower, delta x became smaller, delta p had to get bigger. The momentum of the photons of light had to increase, so the diffraction pattern spread out. Yes?
Little, not off subject, but you talked about Lagrange points.
Yes.
And I remember 30 years ago or more, there was a Lagrange society, and they were pushing for a space station out of Lagrange point. I kind of have the concept of it just being an equilibrium point, but then I believe the Webb telescope orbits around a Lagrange point.
Right.
Can you tell me how that works?
Right. So in this case, all right, the scale's wrong, but say this is the sun, this is the earth. There exist Lagrange points relative to the sun and the earth. Okay? And Webb is at Lagrange point 2, which is out here, beyond the earth. All right? This is called a pseudo-stable point. All right? It's not fully stable. You just can't park there and sit because you still have the earth and the sun that want to pull you that direction. So instead, what the Webb does, it actually kind of does a little loop-de-loop, orbits around that point.
I guess what I'm thinking about is a Lagrange point would seem to be a place where there is no gravity or nothing that you could actually.
Right. Well, no, there's still gravity. Even here,
Gravity, but I mean,
it's just the gravitational, here at the L1 point, the gravitational pull of the Earth is equal to the gravitational pull of the sun.
Right.
So they, in a sense, cancel each other out, but they're still there. If you move just a little bit closer to the Earth, then the Earth's going to pull you in. If you move a little bit closer to the sun's going to pull you in. So, but yeah, we've got a lot of things.
I don't understand the concept of orbiting a
Right.
Lagrange point. I don't know.
Right. Well, I mean, the other thing you got to remember is the Earth, of course, is going around the sun, so these points are all moving around as well. All right, so that's why then it has to take, this is, you can imagine yourself, this is what's called in the rotating frame, right? So again, with the Earth going around the sun, it's like you're hovering and you're kind of spinning as things orbit. So you're basically in the rotating frame itself. So it doesn't look like these two bodies are actually moving. Yes?
Is there a point where they have measured T Coronae Borealis for the size of a white dwarf and how much matter that it's pulling from the other star? Do you know?
Right, yeah. Basically, as I mentioned, let me go back to, yeah, let me go.
I just didn't know if they had measured T Coronae specifically.
Yeah. Let me get to that slide. Next slide, I think. Yeah, here we go. So, yeah, basically, we think the mass is roughly that. That's if you basically use Kepler's laws of planetary or orbital motion to figure out the mass relationship between the two bodies. All right, you can use that to estimate the mass of the objects orbiting each other. Like I said, it's roughly about 1/3 times the mass of the sun. It's close to, but not at the Chandrasekhar limit. Okay? And the red giant is a little bit, like I said, it's a little bit bigger than the sun. Its mass. Its radius, though, the radius of the star is roughly about the radius of Mercury, the orbit. Yes?
What is the luminance of the white dwarf if you were to place it in our solar system?
Generally, white dwarfs, because of their size, of course, as I mentioned, they're hot. They're anywhere from 10,000, 100,000 degrees Kelvin, or not degrees Kelvin, Kelvin. However, because of their size, they're not that luminous. If we put like Sirius B in place of the sun, it's roughly about as bright as the full moon. So it'd be like a full moon night out. Yes?
I think you touched on this already, but what's the expected time frame for the brightening event to occur once it starts expanding?
Like I said, it could happen tonight. It could happen sometime this year is when they're expecting.
When it starts, how long for it to reach maximum?
Oh, a matter, could be hours or days, depending on how fast the reaction goes. So,
Historically, how long has it been?
what's that?
Historically, how long is that duration?
Historically, it's been a couple days. But it's not always the same, like I said, because it's not a regular process that's well-timed and things of that nature. There's variation and things like that that do occur. Some of them tend to be a little more regular than others. As I mentioned, like I said, some have a pretty wide range of decades as far as their outburst variation in the cycle, but some, you could almost set your watch by, or at least your calendar by. Other questions?
So are we more likely to see it on the internet or with the naked eye?
Yeah, you'll probably hear about it before you actually see it. I mean, unless you're out there, you're out there looking at that spot constantly. And the problem is, where it is in the sky now, it sets, I think, by about 1 a.m. or something. Yeah.
So did you hear about the story about Leslie Peltier? So he was an Ohio amateur astronomer, serious amateur astronomer. And he watched the thing faithfully for over 25 years, every night, and it was clear. And one night, it was clear, but he had fallen ill, and he decided that he would allow himself to go to bed. And that's the night that it went.
What's the moral of the story?
Even if you're sick. Right. Yes.
Could you explain the process of how the star consumes itself again?
How the star what?
Consumes itself?
Oh, the deflagration process? Yeah, basically, what'll happen is I didn't give the details, but basically what happens as the layer builds up on the surface, two things possibly happen. Again, if it crosses that critical mass, it'll start a nuclear chain reaction in the core, where it basically fuses carbon into oxygen, and it happens so quickly that it basically rapidly spreads throughout the star and consumes it. There's also the possibility of what's called the double detonation model, where the layer on top, when it detonates, like for a typical nova explosion, instead it sends a shock wave through the star, and it compresses the core just enough to start that nuclear burning of the carbon as well, and then burns and consumes the star that way. So there's two possibilities. And this is the kind of cutting edge stuff right now that they're still trying to figure out and understand. Other questions? Yes.
So back when you had the demo for quantum time, what was the barrier it was tunneling through in the sense?
The Coulomb barrier. Yeah, basically to simplify the model, you basically assume one of the particles is resting and it's creating the barrier, all right? And you basically pretend like the other particle is the one that has all the motion of the combined of the two, and as it approaches the barrier, then it either repulses or it's able to tunnel through to where, again, the strong force will dominate, the fusion reaction happens, and then we have our glorious, beautiful sun up there, or stars, things like that, yeah.
Don, what is the critical mass, and does the white dwarf gain mass over time? This particular...
Well, the critical mass, again, is called the Chandrasekhar limit. It's
No, not the Chandrasekhar limit. The critical mass that would allow it to go nova.
Oh, well, yeah, basically that layer, as I said, it builds a few meters thick, and it's a few thousandths of a solar mass that builds up on the surface. And the rate it falls on the surface varies depending on kind of the geometry of the system, how close the white dwarf is orbiting to the donor star, things like that. So that mass transfer rate can vary from one star to another, one system to another. In the case of T Coronae Borealis, I think it's like a millionth of a solar mass per year is pulled off that star and builds up on the layer, and then, so it's a few millionths of a solar mass that builds up. And again, because of the gravity of the white dwarf, it puts that layer under pressure, and it's at the bottom of the layer that the reaction actually starts.
So I'm leading to the question, the estimated mass of this particular white dwarf was 1.37 solar mass.
Right.
Which is just below the Chandrasekhar limit. If this is not losing mass in the process of going nova, which I don't know one way or the other, will it be building up mass to the point where eventually it'll reach the Chandrasekhar?
Right, that's kind of the cutting edge critical question. Some of the models say that in the case of the nova outbursts, they should be losing mass. It should be not only blasting the material that's built up, but it might be blasting some of the white dwarf material off itself. So these things should maybe getting smaller mass over time. However, if they are building up mass, right, when the explosion happens, it's blowing most of that material off, so there's very few left on the surface.
Well, I assume it happens because type 1a supernovae do exactly.
Right, but there's more than one way to make a type 1a supernova beyond the single white. This is called the single degenerate model, but there's also the double degenerate model where two white dwarfs are colliding and merging together. That turns out to be a pretty common system. Basically that's what these evolved to. Eventually, that other star is going to become a white dwarf itself. And then because these stars orbit each other, each orbit, they move a little closer together because of general relativity. They radiate gravitational energy, and so eventually they spiral in and merge together.
But also they're close because for a time one of them was in the envelope of the other.
Right, and because of drag forces, they spiraled in a little closer together that way too.
Yeah, so that's how they get close to begin with.
Right, exactly. So, yeah, we're not sure yet, though, is this star building up mass with each one of these events, or is it losing mass?
I haven't gotten any evidence one way or the other.
All right. Any other questions? All right, thanks a lot.